Let's continue our investigation of stars by taking a close look at Sirius, the dog star, the canine companion of Orion the hunter. You can't miss it. It's the brightest star in the night sky. Sirius has attracted attention from stargazers for millennia. The ancient Egyptians worshipped it. The Polynesians used it for navigation. And much later, astronomers figured out that it's a nearby main sequence star. In 1844, Friedrich Bessel noticed that Sirius has a friend. He saw that Sirius was following an elliptical orbit and must have a binary companion, but he couldn't see the second star. Then in 1862, a telescope maker named Alvan Clark was testing out his newest creation and managed to spot the companion star. Here's a Hubble image of Sirius and its little friend. We call them Sirius A and Sirius B. The bright halo and the spikes surrounding Sirius A are from diffraction. The star itself is unresolved. You can see why Sirius B was hard to spot. It's just a speck, nearly 10,000 times fainter than Sirius A at visual wavelengths. Over time, astronomers mapped out the orbits of Sirius A and B around their center of mass. The orbital period is 50 years. Star A follows an ellipse with a semi-major axis of 6.5 AU, and for star B, it's 13 AU. What can we deduce from that information? Star B's orbit is twice as big as star A's. And in a binary, mass is inversely proportional to semi-major axis. So star B is half as massive as star A. Does that surprise you? It sure surprised 19th century astronomers. If star B has half the mass of star A, why is it 10,000 times fainter? For main sequence stars, luminosity is roughly proportional to mass cubed. If we double the mass, we should get something like 8 times the luminosity, not 10,000. This is our first clue that there's something funny going on with Sirius B. Let's continue by calculating the total mass. Kepler's third law says that the total mass can be written as a scaling relation. M equals a cubed over p squared, if we measure mass in solar masses, a in AU, and p in years. We also need to remember that a is the semi-major axis of the relative orbit, which in this case is 6.5 plus 13. So we plug in 19.5 for a and 50 for p, giving a total mass of 3 solar masses. Now, if the total is 3, and the ratio is 2 to 1, then the individual masses must be 2 and 1. So Sirius B has 1 solar mass, but its optical luminosity is much lower than the Sun's. A clue about what's going on comes from images at other wavelengths. Let's compare the visible light image from Hubble with an X-ray image from the Chandrasekhar telescope. Wow! In X-rays, the stars reverse their roles. Now Sirius B is the bright one with the diffraction spikes. The reason is that Sirius B is much hotter than Sirius A. Its effective temperature is 25,000 degrees. Wien's law says that the higher the temperature, the shorter the wavelength of the peak in the spectrum. So if you observe a binary at short enough wavelength, the hotter star dominates. Still though, even if you add up all the power from Sirius B, from infrared to X-rays, the total luminosity is mysteriously low, only 2.5% of the Sun's, despite having the same mass. A final clue comes from the radius of Sirius B. We can calculate the radius from the observed luminosity and the effective temperature. L equals 4 pi r squared, sigma T effective to the 4th power. Let's solve for r and write it as a scaling relationship, knowing that when we plug in the Sun's luminosity and its effective temperature, the answer is 1 solar radius. The radius of Sirius B is therefore the square root of 0.025, times the temperature ratio, 25,000 to 5,800, to the -2 power. That gives 0.0085 solar radii. That is tiny. It's only 5,900 kilometers. It's smaller than the Earth. What is this thing? A planet-sized object with the mass of the Sun? Dividing its mass by its volume to get the average density gives 2.3 million grams per cubic centimeter. That's stunning. 1 cubic centimeter, the size of a sugar cube, has the mass of 2.3 metric tons. And Sirius B is not unique. We find similar objects all over the galaxy. They're called white dwarfs. What they are, what sort of material could be so dense, were enigmas for decades. As with so many enigmas, the answers had to wait until the advent of quantum theory. White dwarfs are not fusing hydrogen. They're not fusing anything. There's no internal power source. They're held up against the force of gravity by Heisenberg's uncertainty principle. I kid you not. The electrons in a white dwarf do not collapse into a black hole for the same reason that electrons in atoms do not occupy the same orbits around the nucleus. A white dwarf, roughly speaking, is a giant planet-sized atom with the mass of a star. For ordinary stars, what prevents gravitational collapse is gas pressure. The higher temperature and density toward the center of a star lead to increasing pressure with depth. The resulting outward force opposes the inward pull of gravity, allowing the star to achieve hydrostatic balance. That balance can be sustained because the nuclear reactions keep the center hot. They replenish the energy that diffuses outward and radiates into space. When a star runs out of nuclear fuel, the radiated energy isn't being replenished anymore. So the pressure drops, hydrostatic balance is lost, and the star contracts. When the core is compressed to a high enough density, quantum theory becomes relevant. The star comes up against the Pauli exclusion principle. No two electrons can occupy the same exact quantum state, same position, energy, and angular momentum. The Pauli exclusion principle is the underlying reason for the most basic fact of chemistry. When you add an electron to an atom, you can't put it in the same state as the other electrons that are already there. Instead, adding electrons leads to wider orbits and more complex atoms. It leads to the rules and patterns governing the periodic table of the elements. In a white dwarf, the electrons are squeezed so tightly that the Pauli principle prevents them from occupying the same location in space. That creates a pressure that pushes them apart, but it's a pressure unrelated to temperature. And it's that quantum pressure that keeps gravity at bay. Let's calculate the order of magnitude of the effect. The Heisenberg uncertainty principle says that for any particle, the minimum possible product between the uncertainties in momentum and position is of order h bar, Planck's constant divided by 2 pi. So imagine compressing a cold gas to a density of n particles per cubic centimeter. Each particle is confined to a little cube with a volume of 1 over n, and the uncertainty in each coordinate of the particle's location, delta x, has been squeezed down to 1 over the cube root of n. Heisenberg taught us that the momentum of each particle will not remain zero. It will inevitably range up to values of h bar over delta x, or h bar times the cube root of n. And since momentum is mass times velocity, the velocity will range up to h bar over m times n to the 1/3, where m is the mass of each particle. So at high density, even if the gas is cold and there's no energy source, the particles will be moving. That creates a pressure which can resist further compression. To find out how much pressure, we'll use a result from Lecture 8 when we derived the ideal gas law. The pressure of a gas is the number density times particle mass times the average value of v squared. The same logic applies to this case. And to order of magnitude, we can replace the v in the pressure equation with the delta v that arises from Heisenberg's uncertainty principle, since the particles will have speeds that range from nearly zero to several times delta v. The result is a pressure of order h bar squared over m times n to the 5/3 power. This is called degeneracy pressure. The name always strikes me as unnecessarily negative, as though there's something impure or corrupt about it. But degenerate is simply a mathematical term for a special case in which things that are usually distinct become the same. Here we have a bunch of different particles trying to crowd into the same state. Just for fun, I'll show you the answer we would have gotten if this were a course on statistical mechanics and we'd done everything exactly instead of approximating. It's the same, but with an extra numerical factor in front, equal to about 1.9. That's not so important for us. More important are three things I'd like you to notice about the formula for the degeneracy pressure. First, it's independent of temperature. That's why degeneracy pressure can support a white dwarf even when there's no internal energy source to keep the gas hot. Second, degeneracy pressure varies inversely with particle mass. That means in a neutral gas of electrons and ions, it's the electrons, the low mass particles, that produce almost all of the degeneracy pressure. Third, degeneracy pressure varies as the 5/3 power of density. That's a stronger dependence than ideal gas pressure, which varies as density to the first power. So if we crank up the density, eventually degeneracy pressure will dominate over gas pressure. Now, let's try to build a star using degeneracy pressure. In the last lecture, we constructed models for main sequence stars by setting the outward force from the pressure gradient equal to the inward force of gravity. Let's do the same thing now, but using degeneracy pressure instead of ideal gas pressure. We need to satisfy the equation of hydrostatic balance. dp dr equals minus rho times gm over r squared. Let's replace this differential equation with the algebraic approximation that we derived last time. The central pressure is on the order of the average density times 2gm over r. But this time, instead of using the ideal gas law, let's set Pc equal to the degeneracy pressure. Let's think a minute about the meaning of the little m and the n on the left side. Since degeneracy pressure varies inversely with mass, and electrons are 1,800 times less massive than protons, the electrons provide almost all the degeneracy pressure. So for little m, we'll insert the electron mass, and for n, the electron number density. On the other side of the equation, we have rho, the mass density. That's dominated by the ions. So we need to be careful. The electrons provide most of the pressure, but the ions provide most of the mass. That makes the relationship between n and rho subtler than before. Let's suppose our white dwarf is made of carbon and oxygen. We'll see later why this is a good assumption. Carbon has 6 electrons, 6 protons, and 6 neutrons, an atomic mass of 12. Oxygen has 8 electrons and an atomic mass of 16. In both cases, there are twice as many nucleons as electrons. That means for every 1 electron, there are 2 nucleons. If the electron number density is n, then the mass density is 2 proton masses times n. We can use that relationship to rewrite n in terms of rho. Another subtlety is that the left side of the equation refers to the central density, but the right side refers to the average density. As we did before, let's make the crude assumption that the central density is twice the average density. That'll cancel the 2 on the right side of the equation. And now, let's bring all the constants over to the left side of the equation and the stellar properties to the right side. The right side is now m over r times rho to the 2/3. m, r, and rho are not all independent. Rho is m divided by 4/3 pi r cubed. For simplicity, let's just say m over r cubed. We've already been very cavalier about 2's and pi's. Then the right side simplifies to r times the cube root of m. And we can solve for r, leading to an expression for radius as a function of mass. It looks a little neater if we express the stellar mass in units of the proton mass. Do you notice anything strange about this result? R is inversely proportional to the cube root of m. Increase the mass, and the radius goes down. This violates common sense. When you add more snow to a snowball, it gets bigger, not smaller. But when you add more mass to a self-gravitating ball of degenerate particles, it gets smaller. Here's why. When you add mass, you increase the gravitational compression. For degeneracy pressure to compensate, the particle velocities need to go up. And from Heisenberg's principle, the way to force delta V to go up is to make delta X go down, shrink the spacing between the particles. So you end up with a smaller and denser star. Let's run the numbers for an object with the mass of the Sun. One thing though, we derived this formula with blatant disregard for factors of 2 and pi. The exact answer turns out to be bigger by about a factor of 3. When you make that correction and plug in all the numerical constants, you get an R of about 5,800 kilometers, just what's observed for Sirius B. And studies of large samples of white dwarfs confirm the amazing truth that the bigger the mass, the smaller the size. By this point, you're probably wondering, where do white dwarfs come from? So let's talk about the origin of these exotic objects. A star like the Sun has enough hydrogen to last about 10 billion years. At that point, the core has been converted entirely to helium. Fusion stops. The gas pressure starts to go down, and the core contracts. This causes the density to rise, and less obviously, it causes the core to heat up. Gravitational contraction releases gravitational potential energy, which is converted into heat. This is a remarkable and seemingly paradoxical property of all stars. When they lose energy, their cores heat up. We're used to adding energy to heat something up. When you cook soup, you put it on the stove. But if you want to cook a giant self-gravitating sphere of soup, just put it outside and let it radiate away energy. It'll contract and heat up. The jargon here is that gravitationally bound systems, like stars, have a negative heat capacity. Back to the story, though. The star runs out of hydrogen. The core contracts and heats up. Eventually, the core gets dense and hot enough to ignite helium fusion. At a temperature of around 10 to the 8 Kelvin, helium nuclei have enough kinetic energy to collide and make beryllium-8, which is a very unstable nucleus, but if there are enough helium nuclei around, there's a chance that one of them will hit the beryllium nucleus hard enough to make carbon-12. So carbon starts accumulating, and sometimes fuses with helium to make oxygen-16. Meanwhile, strange things are happening higher up in the star. For reasons we'll discuss in the next lecture, the outer part of the star swells up to 100 times its usual size. The star becomes a giant. Eventually, the outer layers rise so high and become so weakly bound to the star that they get pushed out into space by radiation pressure. The hot, dense core becomes fully exposed to the universe after billions of years of being hidden away. And by this point, the core is so dense that degeneracy pressure is sufficient to oppose gravity. So it stops contracting, and there's no way to ignite any further nuclear reactions. Once the helium runs out, the core becomes an inert ball of carbon and oxygen. That's a white dwarf. It starts out white hot, but gradually cools and fades to black over billions of years. That's what's happening to Sirius B, and it's the fate that awaits the Sun. Might sound a little depressing, but there is a consolation. While the white dwarf is still hot, all those ultraviolet and X-ray photons stream out and light up the surrounding gas. What used to be the star's outer layers now form an optically thin cloud, which displays an emission line spectrum. The white dwarf is now surrounded by a wispy, glowing sphere. In a rational world, we'd call this a white dwarf nebula. But in the real world, it's called a planetary nebula, even though they have nothing to do with planets. It's because our predecessors, who didn't know what was going on, thought they looked sort of like planets. Some planetary nebulae glow in vivid colors, depending on the composition, the density, and the temperature of the gas. They're among the most beautiful objects in the galaxy. And it's fun to keep in mind that in the center of each one is an outrageously dense object, millions of grams per cubic centimeter, which was once the core of a sun-like star burning hydrogen for billions of years, and now supported only by degeneracy pressure, a macroscopic manifestation of Heisenberg's uncertainty principle. Many planetary nebulae are spherical, as you might expect, but others have strange shapes. Some have a rectangular appearance. Others look like two wings joined together, like a bird or an insect. Those might be from binary white dwarfs, with the orbital motion of the two stars sculpting the surrounding gas. The truth, though, is that although we have a great theory to explain the interior structure of white dwarfs, we can't always explain the artistic shapes that they paint with their high-energy radiation. Let's return to the theory of white dwarf structure. I want to point out a flaw in our earlier calculation, an assumption that we made that's not always true. We started by saying that when Heisenberg's uncertainty principle starts to become relevant, the uncertainty in momentum is h bar times the cube root of the number density. And since delta p equals m times delta v, then delta v also varies as n to the 1/3. That equation implies that if we keep increasing the density, we can make delta v as high as we want. But that can't be true. The universe has a maximum speed, the speed of light, a fact that's sewn in to Einstein's theory of relativity. So as delta v approaches c, the formula must break down. Let's figure out when this problem occurs. We'll set delta v equal to, say, half the speed of light, and then we'll solve for the critical value of n. It comes out to be mc over 2h bar, the quantity cubed. To get the corresponding mass density, we multiply by 2 proton masses. And numerically, it comes out to be 7.3 million grams per cubic centimeter. Above that density, we need to take relativity into account. Now, earlier we found the density of Sirius B, a 1 solar mass white dwarf, to be 2.4 million grams per cc. That's lower than the critical density by a factor of 3. So our approximation was probably okay for that case. But density increases with mass. White dwarfs of larger mass have higher densities. So there must be some critical mass for a white dwarf, above which the electrons start moving close to the speed of light. Let's calculate that critical mass. We'll start with the mass-radius relationship that we derived earlier. R is proportional to m to the minus 1/3 power. What does that imply for the relationship between density and mass? Density is proportional to m over r cubed. And for a white dwarf, r is proportional to m to the minus 1/3 power. Together, these imply that density goes like mass squared. Now let's think. We said the density of a 1 solar mass white dwarf is 3 times lower than the critical density. To raise the density by a factor of 3, we need to increase the mass by a factor of √3, or about 1.7. So we would expect the critical mass to be around 1.7 solar masses. That's not that high. It seems realistic that the core of a star could exceed 1.7 solar masses. So we'd better figure out how to repair our calculation. We need a new formula for degeneracy pressure for the case in which the particles are moving close to the speed of light. That doesn't sound easy, but we can do it. Stick with me. Do you remember when we derived the ideal gas law back in Lecture 8? We started by imagining a gas in which particles move in only one direction, say the x direction. Let's do the same thing, but this time all the particles move with the same speed, c. What pressure would they exert on the wall? When a particle hits the wall, it reflects, changing its momentum from p to minus p. And since momentum is conserved, the wall absorbs a momentum of 2p. Now consider the momentum absorbed by an area, delta A, of the wall. In a time delta t, it absorbs a momentum of 2p times n over 2 times c delta t delta A. That first factor, 2p, is the momentum transferred per collision. The second factor, n over 2, is the number density of rightward moving particles. And the third factor is the volume of space within which a particle is close enough to hit the wall within a time delta t. Pressure is force per unit area, or momentum per unit time and area. So we divide by delta t delta A, giving pnc, where p is the momentum of each particle. For degenerate particles, we know from Heisenberg's uncertainty principle that delta p is of order h bar times the cube root of n. Inserting that for p, we find that the degeneracy pressure is of order h bar c times n to the 4/3 power. That's the formula we need for particles moving near the speed of light. The old non-relativistic formula went as n to the 5/3 power. This new one goes as n to the 4/3. The pressure doesn't increase as rapidly with density. This will turn out to be bad news for a massive white dwarf. When you pile more mass onto a white dwarf, increasing the gravitational force, the only way it can re-establish hydrostatic balance is to become denser. That way the particles are pressed closer together, and Heisenberg's uncertainty principle leads to higher velocities and higher degeneracy pressure. But above the critical mass, the particle speeds can't increase anymore. They're already at the speed of light. That's why the degeneracy pressure starts rising more slowly with density. The white dwarf is having a harder time fending off gravitational collapse. Let's see if we can still achieve hydrostatic balance. We'll take our equation expressing the condition of hydrostatic balance. Pc is of order rho average times 2gm over r, and insert the new formula for degeneracy pressure. In the interest of time, we'll aim straight for the scaling relation between m and r. We'll ignore the 2's and the pi's and neglect the difference between rho central and rho average. And as before, we'll replace the electron number density with rho divided by 2 times the proton mass. But we won't bother with the 2. Then we'll bring all the physical constants over to one side and the stellar properties to the other side. And since we're interested in the mass-radius relation, we'll replace rho by m over r cubed. A dramatic thing happens here. The r's cancel out. There's no radius anymore in the equation. There's just mass. Apparently, there's only one possible mass for which we can achieve hydrostatic equilibrium. Solving for that unique value of m leads to an elegant collection of fundamental constants. My favorite way to write it is as a dimensionless number times the proton mass. And the dimensionless number is a sort of greatest hits collection of fundamental constants. There's h bar times c over the gravitational constant times the proton mass squared, all to the 3/2 power. Plugging in the values of those constants, this number turns out to be 2.2 times 10 to the 57. And the mass itself is 1.8 solar masses. A more rigorous calculation that does keep track of all the 2's and the pi's gives a somewhat smaller answer, 1.4 solar masses. This glorious combination of fundamental constants and that critical mass of 1.4 is called the Chandrasekhar limit, named after Subrahmanyan Chandrasekhar, a legendary astrophysicist who derived it in the 1930s. What is the meaning of the Chandrasekhar mass? It means that relativistic degeneracy pressure can only balance gravity for that one specific mass. Less massive stars are less dense, and the electrons aren't moving at the speed of light, so we go back to the case of non-relativistic degeneracy pressure, the case we worked out earlier. But more massive than 1.4 solar masses, and the electrons are moving near the speed of light, and it's impossible to achieve hydrostatic balance. Gravity compresses the star, causing it to contract, which earlier would have caused the electrons to speed up, but they can't speed up anymore. They can't produce enough pressure to withstand further collapse. You can see the effect on a chart of radius versus mass. The curves are exact solutions of the equation of hydrostatic equilibrium for a cold, degenerate gas. One curve shows the relationship we derived for low-mass white dwarfs. R goes like m to the minus 1/3. But this curve ignores the effects of relativity. When you include relativistic effects in the theory, you get the other curve. At low masses, the two curves are very similar. But as the mass approaches the Chandrasekhar limit, the relativistic curve starts dropping. The radius is shrinking. Gravity is winning. And at 1.4 solar masses, the radius drops to 0. What does that mean? What actually happens if the core of a massive star exceeds 1.4 solar masses? I'll end this lecture with a quotation from Chandrasekhar himself, from the end of his most famous paper. It must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. For a star of small mass, the natural white dwarf stage is an initial step towards complete extinction. A star of large mass cannot pass into the white dwarf stage, so one is left speculating on other possibilities.